This is lessons 5.3 and 5.5. We're going to be talking about proving triangles are congruent. So we already know that if all parts of triangle match, all three pairs of sides have a partner, all three pairs of angles have a partner, the triangles are congruent. But there's shorter ways to do that, and we're going to learn about 5 different shortcuts in total. The first one is called SSS, or side-side-side congruence. And in that case, if you can see that 3 pairs of sides are congruent, that automatically makes the triangles congruent. So if segment AB was congruent to segment DE, which was a side, if segment BC is congruent to segment EF, that's another side, and if segment AC is congruent to segment DF here with 3, the third side, then the triangles themselves are congruent. So I can make my congruent statement of triangle ABC is congruent to, so now A was between 1 and 3, D is between 1 and 3, D, E is between 1 and 2, B is between 1 and 2, E, and then F. The next shortcut is called SAS, or side angle side congruence theorem. So that's when we have 2 sides that match and what we call the included angle. And by included angle, we mean if I were to draw or trace the 2 sides that are marked as congruent, it forms or points to the corner where the angle is congruent. So when I have the 2 sides here, between them is the angle. So that is segment AB matching segment DE as a side, angle B being congruent to angle E as an angle, and then segment BC congruent to segment EF as our other side. That's SAS, which would make triangle ABC congruent to triangle DEF. Now, there is a different instance if the angle was not between the 2 sides. And that's not allowed for many reasons. So ASS or SSA doesn't work. And the reason is the third side could be big or the third side could be small. You notice in these 2 pictures, they both have the same exact angle here. They both had this side congruent to this side and this one congruent to this one. But depending on how we bend that last line, going outward or going inward, that could change the third side of them. So it doesn't work for normal triangles. But it can work if it is a right triangle. So HL stands for hypotenuse leg. And that's going to look like ASS or SSA, but in a right triangle. The hypotenuse is always defined as the side across from the right angle. So if I draw an arrow from the right angle, it points to the hypotenuse. So in this case, it would be segment BC and segment EF. And then the legs are one of the other 2 remaining sides. So in this case, it's segment AB and segment DE. So only knowing these pieces of information, along with the fact that it's a right triangle, would allow us to say that triangle ABC is congruent to triangle DEF. So what's allowed to be marked congruent in a triangle? When we have a picture where one of the sides is part of 2 different triangles, we consider that a shared side. And if we think about why we would be allowed to say that segment AC is congruent to segment AC, that's the reflexive property. So a shared side is really a reflexive side, and we're always allowed to say that that's congruent without them having to tell us that we need to say it. All right, we do need to make sure we mark it and say it if we're doing a proof, but it's not something that needs to be given to us or pre-marked for us. The same is true about vertical angles. So in our picture here, I would be allowed to mark vertical angles congruent, and that would be the vertical angle theorem that allows us to do that. If we have a right angle that's a linear pair with another angle, that second angle would also be a right angle. And that's based on the definition of perpendicular. When you have a right angle on one side, right angles are formed everywhere because what it means to be perpendicular is to form right angles. And then if we have parallel lines, we can have angles that are congruent, like angle E and angle H being congruent based on my lines being parallel here, or angle BAC and angle DCA because of my lines being parallel here. So in both of those instances, we ended up with alternate interior angles. So we could use the alternate interior angle theorem to say that those angles are congruent. So these are the only things we're allowed to add to a picture without them telling me more information. And that's always going to be my first step when I go to decide if triangles are congruent. So that is what I'm doing here. Example 1, decide whether the triangles are congruent, explain why or why not. If they are, finish the congruent statement. So I'm right away going to mark a shared side in this picture. I can mark a shared side in this picture, and I have a shared side down here, MK, in the third picture. I have vertical angles in this picture. I have a right angle on one side, so I have a right angle on the other here. And I had parallel lines here. This is a case that's not going to happen often. These are not alternate interior, but in fact, corresponding angles. That's why we did it as an example and not a try. So all of those things we were allowed to mark before we did anything else. And now that I have them marked, I'm going to determine if the triangles are congruent. Any place I see a dash represents a congruent side. So in this figure, I had 3 sets of dashes on my triangle. That means I'm left with S, S, and S, which is one of the ways to say that triangles are congruent. And the second triangle does in fact match the first, which is something that has to happen as well. So these are congruent by SSS. And for my congruent statement, I had GAD, so top along one across. So that would be JAD to finish our congruence statement. For the next picture, these dashes represent a side, this dash represents a side, and this curve represents an angle. So what this tells me is that the two sides don't point to the angle. So this wouldn't count as SAS. This would look more like SSA or ASS. And then if it looks like ASS or SSA, we're checking to see if they were right triangles, which they weren't. So this is just no, because SSA is not allowed. And we're not going to bother finishing the statement because they're not congruent. For C, we have a side, we have a side, we have an angle again. Once again, these two sides don't point to the angle, so this would look like SSA. But the difference now is that these are in fact right triangles. So instead of being an S and S and an A, this is really the hypotenuse, and this is really the leg. So this is congruent by HL. And we could say the triangle EBH, so E was the far one, K, so KBH. In problem D, these dashes represent a side, this dash represents a side. This had nothing to do with that S. This had to do with parallel, not with the congruent that we were also told. And this curve represents an angle. So I have again 2 S's and an A, and if I connect the two sides, it points to where my A was. So SAS will work for this one. And if I called it NQT, I started with the angle with one curve, so that's TQT. ZW. The final one is probably the trickiest one. When I have pictures that really truly overlap like this, I tend to redraw them and I separate at least one of them. So this was J, this was M, and this was K. I know on MK I marked that with 2 dashes. I know JM was marked with a dash, and there was a curve here by the M. So here I have 2 S's and an A. And if I connect or redraw the 2 sides I labeled with S, it pointed to my A. So this is SAS. And I can continue JMK, which is what I had here, would match with LKM. So here's a set of 4 for you to try. You can pause it now if you'd like. The answers are posted on Classroom. Not only can we just determine if triangles are congruent, we can prove that they're congruent. So here we're going to do a proof. We are given that B is the midpoint of AP, so let's include that. B is midpoint of AP was given. And we also were given that segment AM is congruent to segment PM, which was down here in step 3. We know the final thing should be that the triangle AMB is congruent to triangle PMB. So now let's go through our proof. If we were given that B was the midpoint of AP, and I'm now saying that segment AB and segment PB are congruent, that's because of midpoint. Definition of midpoint. We knew that segment AM and segment PM were given as being congruent, so I'm going to mark those in my picture as well. And now we have segment MB congruent to segment MB. That is something congruent to itself, which is reflexive. So the final step is to say that the triangles are congruent. And in our proofs, that step will always be our shortcuts. So far, we have SSS, SAS, and HL. This one, if I look at what I've labeled in my picture, would be SSS. It's going to be incredibly important to label the pictures with what's congruent in your proof, so when you get to the step of the triangles being congruent, you have a clear picture of what that reason should be. So here's check-in number 2. You can pause now and try it. Answers are posted on Classroom. For example 3, I'm given 2 givens again. BC being parallel to AD is listed in step 2. So we would include the other given from step 1. Segment BC is congruent to segment DA. If I know I had lines that are parallel, I'm using angles that are congruent, and they specifically said the alternate interior angle theorem. Tracing out the parallel lines with the transversal puts me into this corner here and this corner here. So that's angle BCA is congruent to angle DAC. And the next step says that segment AC is congruent to segment CA. So they did flip the letters around, but they're still saying the exact same segment on both sides. So that is still the reflexive property. And my last step, I know that I'm talking about congruent triangles. And in my picture, we had this as an S, this curve is an A, this dash is an S, and connecting my 2 S's together pointed to A, which makes SAS. Here's the next one for you to try. Pause it now if you'd like. The answer is posted on Classroom. Example 4. We're given that segment AC is congruent to segment DC. And step 2 also says given, and that's that angle ABC and angle DBC are right angles. So in the next step where I say that I have right triangles, I'm saying that because I had right angles. So that is actually the definition of right triangle. So we call something a right triangle if it contained a right angle. The next step says we're going to use the reflexive property. So in this picture, the side that's connected to both triangles is CB. So we can say segment CB is congruent to segment CB by our reflexive property. And the final step is our proof statement. Oops, ABC is congruent to triangle DBC. And normally this would be an S, an S, and an A, but that would look like ASS or SSA, which we know is not allowed. But because we called them right triangles, I can instead use the other labels of H and L. Anytime we want to use HL in a proof, we will have to define the two triangles as right triangles. So that should be a hint to you. If we've declared that we have right triangles in our proof, we will likely be using HL to prove the triangles are congruent. So here's another check-in for you to try. Pause it if you'd like. The answer is posted on Google Classroom. And now we just have a proof to do that. Now there's no expectation. We've done one of each proof, one for SSS, one for SAS, and one for HL. So this could be anything. So let's look at this. We have segment WX bisects angle ZXY is given. And also segment ZX and segment YX are congruent is also given. But I'm going to use the definition of bisect. So I'm doing these two angles would be congruent to each other because the big angle was being bisected. It was being cut in half. So I'm going to call that angle ZXV is congruent to angle YXV by definition of bisect. I also see in step 4 it says reflexive property. This segment right here is the one that's part of two different triangles. So I can say that segment XV is congruent to segment XV. And my last thing will be to say the triangles are congruent. Triangle ZXV congruent to triangle YXV. There is something we haven't marked yet in this picture, and that was our other given. ZX was congruent to XY. So now in the triangle I have here, I have this side, I have this side, and I have this curve for an angle, and connecting those two S's pointed at the A, so that would be SAS. There's one final check-in for you to try. You could pause now if you'd like and check your answer on Classroom, but that is also the end of sections 5.3 and 5.5.